Hello and welcome to Unit 8, Kinetics and Equilibrium, Lecture D. Today we're going to talk about Le Chatelier's principle. Last lecture you learned that some reactions are reversible. That means the forward reaction and the reverse reaction can happen if we have a closed system and you're not losing one of the species in the equation. Today we're going to talk about how you can change that equilibrium point. So just to review, equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. It's not about concentration or how much there is, but how fast the two reactions are going. Le Chatelier's principle says that we can change that equilibrium point. You can push a reaction so that there is more product or more reactant. You can shift it in either direction depending on the conditions that you put it under. The reason you might want to shift an equilibrium point if you're in industry and you're trying to make more of the product because that's what you would sell, you would want to shift your reaction to make more products, or we call that shifting it to the right. If it's maybe an environmental issue and you want less of your reactants, you might want your reaction to go slower. So in that case, you would shift your equilibrium to the left so that there are more reactants instead of products. Generally, Le Chatelier's principle, you can see it there. They talk about stresses and stressing the system at equilibrium. But if you just memorize that you're always moving away from an increase and towards a decrease, you're going to be all set. So in Le Chatelier's principle, we look at an equilibrium reaction. So this first one where I have solid iron and steam, so that's going to be a gas, turning into ferric oxide and hydrogen gas over here. Since we are working with two gases, this would have to be an enclosed container in order to reach equilibrium. Otherwise, the gas would escape and your reaction would go to completion. If I want more of this hydrogen, maybe I could increase the amount of iron. So it reaches equilibrium, and somehow into this closed container, I drop more of my solid iron. So I increase the concentration of the iron. We would shift this reaction to the right. It would use up, so there would be less of the water available, and it would make more of this ferric oxide and more of the hydrogen gas. So we shift away from what we increased. Let's say we want to actually make more hydrogen, and we have plenty of iron and water, steam in our system. We just want the reaction to go faster. One of the things we can do is decrease the amount of hydrogen. So if you have a valve on your closed container and you remove the hydrogen gas, you just open up the valve and take some of the hydrogen out, the system is going to want to replace what you removed, so it's going to move towards your decrease. And we say it again shifts to the right. That means you're going to have less iron and less steam, and you're going to make more of your ferric oxide. You generally won't talk about the amount of what it is you're removing because you're artificially changing that amount, but it will make more hydrogen as it goes to the right. We can also shift this reaction left. We could do the same thing. If this is steam, we could remove our water by opening up the valve. So if we're removing the water, somehow letting this dry out, it's going to then shift towards what you're decreasing, and we say that it shifts to the left, which means there will be less of the ferric oxide and less of the hydrogen produced, and we will get more of the pure iron. Away from an increase towards a decrease, and you're all set on Le Chatelier's. So concentration, easy enough, you just add or remove product. We have this thing called the common ion effect, which is a little more confusing. Remember that sometimes when we add a solid ionic compound to our aqueous systems, because most chemistry is done in an aqueous solution, our ionic compound dissociates. So when we have solid silver chloride in water, it's going to dissociate into silver ions and chlorine ions. Any other ionic compound that we add to this aqueous solution then is also going to dissociate into its ions. So if I add sodium chloride aqueous, what I'm really adding here are sodium ions and chlorine ions. There is no sodium in our equilibrium equation up here, but there are chlorine ions. So what I'm really doing, let me get rid of this arrow, is I am increasing the concentration of the chlorine ions. So if I'm increasing chlorine ions, it's going to shift away from that increase. We say that it shifts left, which means I will have less of the silver ions and more water and more of the pure silver chloride. So if we just look at this first equation here, we're not going to look at all of them, but these are some example equilibrium equations. If I look at this first one, if I want to make more of my solid calcium carbonate, I could add something like calcium chloride. If I add that to our aqueous system, it's going to actually split apart, and what I'm really adding are calcium ions and chlorine ions. There are no chlorine ions in our equation, so we just ignore them. There are calcium ions, so I'm increasing the concentration of my calcium ions, which is going to shift this reaction to the right, which means there will be less of the carbonate and more of the calcium carbonate being produced. I keep saying that reactions go to completion. If we make something that is a solid precipitate or a gas and it's not in a closed system, then our reactions may go to what we call completion, which means you will have a one-way arrow and the reaction stops. So if we use up all of our reactants and there is no product that can go backwards, so if we look at our example equations before, if we look at this one right down here at the bottom, if this is in a closed container, it can be at equilibrium. If I put this in an open container, this carbon dioxide gas can be released, and then there'll be no CO2 left to do the reverse reaction, and it will go to completion. This is what happens when you forget to put the lid back on your pop bottle and all of your aqueous carbon dioxide in your pop, the carbon dioxide comes out and your pop goes flat, and all you have left is now sugar water. And again, away from an increase towards a decrease. I've repeated that probably 10 times already, so it's probably pretty important. Speaking of pop, and what happens to those equilibrium equations, we need to talk about the effects of pressure. Pressure is only going to affect the equilibria of gases. So when you look at an equation, it's important that they put the phase of matter into them, and pressure will only affect gases, and it has to do with the number of moles of gases in your equation. Remember that every 1 mole of gas has a volume of 22.4 liters. So the amount of gas will affect the pressure on the system. If you have a container with rigid sides and you put 22.4 liters of gas in it, it will exert a certain amount of pressure on the sides of the container. Take that same sized container and put 44.8 liters of gas in it, and the pressure will be greatly increased. So your system is going to try to make more or less moles of gas to return the pressure back to standard pressure, whatever the pressure was in the container when it was at equilibrium. So if we look at making ammonia, which is really important, and this Haber process shows up as an example because producing ammonia is industrially very important, so they use this as an example a lot. We have 1 mole of nitrogen on the left plus 3 moles of hydrogen, and it's at equilibrium with 2 moles of ammonia on the right. So I have 4 moles of gas on the left of my equation and 2 moles of gas total on the right. And our away from an increase towards a decrease still works. If we increase the pressure, it's going to have to move to the side that makes fewer moles of gas so that we can get away from the stress of the increased pressure. So if we increase pressure, it's going to move to where there are fewer moles. And if we decrease the pressure, it's going to move towards where there are more moles of gas in order to get the pressure back to where it was. So in our Haber process, if we increase the pressure, it shifts to the right because it favors fewer moles of gas, so it'll favor the 2 moles. If we decrease the pressure, it will shift to the left and make more pure nitrogen and pure hydrogen because that favors more moles of gas. Industrially, then, when they make ammonia, they keep it under pressure because they want to make as much NH3 as they can. Let's look at the equation. I added an equation here in the blank space with carbon dioxide. I had said when we were looking at example equations that this right here, this equation that we looked at last, is the one that involves POP. So the carbonic acid turning into carbon dioxide and water. And I'm going to tell you right now that the equation I just wrote here is exactly the same. And it doesn't look like it, but if we look at reference table K briefly, reference table K shows us acids. So if we look down here really quick at what carbonic acid is, it is water plus carbon dioxide. And when you put the two together, you get H2CO3. So carbonic acid is really carbon dioxide attached to water. I wrote the equation out this way so that we can look at the moles of gas and apply the Le Chatelier's principle about pressure to the equation. I have 1 mole of gas on the left, and on the right, once it's aqueous, there are 0 moles of gas on the right. When they make your pop at the factory, they put it under pressure because when you increase the pressure for this particular equation, it's going to shift your equilibrium to the right because there are 0 moles of gas on the right, and 0 moles is less than 1. That makes your pop carbonated. When you open the lid and you hear the fizz come out, you're decreasing the pressure on your pop bottle, which is going to shift this equilibrium to the left. And as it shifts to the left, because there are more moles of gas there, then your pop goes flat. One of the things you have to watch out for is that you are truly counting the number of moles of gas correctly. So if we look at this other industrial equation, which is making hydrochloric acid, HCl is very important for industry, you have 1 mole of hydrogen gas on the left with 1 mole of chlorine gas producing 2 moles of HCl. So basically you have 2 moles of gas on the left and 2 moles of gas on the right. So as far as producing hydrochloric acid goes, they keep it in a pressurized container so that the particles will collide with each other more, but you really don't shift the equation in either direction, so to continue increasing the pressure would make no difference on its equilibrium point. The last factor that we're going to talk about that affects equilibrium will be temperature. And again, we're going to treat heat and temperature like anything else with Le Chatelier's principle, away from an increase towards a decrease. So you're looking for where the heat is. So if I increase the temperature, and sometimes they'll say they've increased the heat, or they'll say that they added joules or kilojoules of energy. In this specific example, it's calories. All of those things represent heat. If I've increased the heat, I'm going to shift away from the increase, which means it would shift, in this case, to the left. And that means I would make more of the nitrogen and more of the hydrogen, and there would be less of the ammonia. So we say that increasing the temperature favors the reverse reaction in this case. If I cool the system, if I decrease the temperature, remove heat, cool it, this particular equation is going to shift then to the right, because it's going to try to replace the heat that we've taken out, which means that there will be less nitrogen and less hydrogen and more of the ammonia. Increasing the temperature favors the endothermic reaction because it's going to try and cool the system off, and decreasing the temperature favors the exothermic reaction because it's trying to make or release more heat to return the temperature back to where it was. There is a footnote here back a few lectures where we just talked about speeding up reactions in general. We said that increasing the temperature increases reaction rate, and increasing the temperature will increase both the forward and the reverse reaction. Industry looks for the point where increasing the temperature speeds up both the forward and the reverse reaction, and then stop at the point where they start to lose the product that they're looking for. So when they hit the temperature that the reverse reaction starts going faster and they're actually making less product, then that's the optimal temperature. And for something like the Haber process, the optimal temperature is about 500 degrees Celsius, so it's not exactly cold. If we look at some other equations, they can make these a little more difficult by not writing the heat into the equation for you, but giving you the delta H instead. Remember that we said on reference table I, if the delta H is negative, then your reaction is exothermic. So if this delta H is negative, it's exothermic. Heat goes on the right as a product. This one's negative, so heat would be on the right as a product. This last one is positive, so heat would be on the left as a reactant. So this first example, if I increase the temperature, it's going to move away from the increase, so it's going to shift left. This one also, if we increase the temperature, it's going to shift left. And the last one, if we increase the temperature, it's going to shift to the right. So if we increase the temperature, it's favoring the endothermic reaction, so that's why it's shifting left, favoring the endothermic reaction, favoring the exothermic. Last in your notes is the effect of a catalyst on equilibrium, and that is just that it does not do anything. Adding a catalyst will help a reaction reach equilibrium faster, but once it's at equilibrium, it will not shift the point at all. And that's all you have to remember about catalysts as far as equilibrium goes. And that's it for Lecture D.